There was a little delay. All right. I am pleased to introduce the speaker for our final LPL colloquium of the academic year. Save the best for last. Krista Soderlund, she comes to us from University of Texas Institute for Geophysics, where she's a research scientist. I've known her for 8 years. She started out there as a postdoc, and she's been working her way up the ladder. Let me see. She got her bachelor's from Florida Institute of Technology in a double major in physics and space sciences, and then she went on to UCLA to get her master's and PhD. She has been known prior to her more recent work in oceans on outer satellites. She's very well known for work in planetary dynamos. She can solve the magnetohydrodynamic equations in her head. I can barely say the word. She's on the Reason science team for the Europa Clipper, radar sounder, and the RIME science team for JUICE. So she's got both RIME and Reason. And since she's good at Reason, she was on the Ice Giants science definition team and some other science teams for various mission proposals. She worked on VIMS for Cassini, and she's done field work in Antarctica with doing aerogeophysics. I have a hard time with that one as well. And also ship-based physics in the South Pacific. So anyway, she's going to talk to us about ocean dynamics of outer solar system satellites today. So let's give Krista a warm welcome.
All right. Great. Thanks, Jack. Is the volume working okay? It sounds like it. Okay, thanks very much for the invitation and also the very kind introduction. So as Jack mentioned, I'll be talking about ocean dynamics in the outer solar system. And before we get started into that, I wanted to acknowledge my collaborators. First is Brittany Schmidt, who was actually here at LPL as an undergrad, and then also Johannes Ficht at the Max Planck Institute, and then finally Don Blankenship at UTIG, who I did my postdoc with. And we're able to do this with funding through NASA. So the talk's going to be broken into 3 parts. The first is going to look at ocean worlds and why they're so important for habitability. But the bulk of the talk is going to focus on the ocean dynamics. And to do that, we're going to use both rotating convection theory in combination with numerical models looking at how the fluid circulations could be going on in these bodies, and then think about how these circulations could influence ice-ocean coupling processes and even some processes within the ice shell and on the surfaces of these bodies, and then wrap up. So I just wanted to reiterate that ocean worlds are becoming more and more prevalent in our solar system, and they're also really important targets for habitability. So here's just a quick summary and schematic of all of the likely ocean worlds in our solar system. And the 4 cases that are the most promising in terms of having a global subsurface ocean are Europa, Ganymede, Enceladus, and Titan. So these are going to be the ones that I focus on in the talk today. So I want to lump together Europa and Enceladus because they're both relatively small bodies. So they're able to have their global ice shell on top, a global ice liquid water ocean beneath that, and then these oceans are in direct contact with the rocky seafloor below because they're relatively small bodies. So this is exciting for habitability because these are located pretty close to their host planets. So these planets have really strong magnetic fields, so they're going to irradiate the surface. And then there's going to be radiolytic processing of this ice that then causes there to be reductants formed on the surfaces of these satellites. And then conversely, on the other hand, if you have enough tidal activity going on within the mantles of these bodies, you could have magmatism, and because it's in contact with the water above it, you could have this hydrothermal circulation going on at the base of the ocean, which could produce reductants. And in order for a really important energy source for potential life is redox reactions, which would require these basal reductants and these surface oxidants to combine, which would then produce this energy source. But in order for that to happen, you need to have some type of communication from the seafloor across the ocean and then also across the ice shell. So we don't know if it's going to go up or if it's going to go down. So this exchange process between these materials is a really important aspect to consider. And this scenario is really similar on Titan and Ganymede, with the notable exception that these are larger satellites. So they are under higher pressures at the base of their oceans. So you could potentially have, or likely have, layers of high pressure ice at the base of the ocean, as shown here. So then you're going to have a separation between the rocky mantle and the liquid water above it. However, it's thought that this high-pressure ice layer could be unstable to convection, and it's also going to have a lot of two-phase flow within this convective region, so you could have potentially quite a lot of fluid exchanged between the mantle and the ocean anyways, so it doesn't seem to be a prohibitor of any potential redox reactions, assuming you can still get across the ocean and the ice shell above. So as I mentioned, one important aspect of this is that you need to have the oxidants and the reductants combined. So that means that the circulation within the ocean, and then also how you could have the circulation within the ice shell itself or some other mechanisms to get material from the surface of the ice shell down into the ocean, are really important aspects to consider. And I focus primarily on the ocean side of things. And there are three main ways that you could generate ocean currents that will be a big driver in this exchange process. And the first is convection, so that's basically just due to buoyancy perturbations that could be due to temperature or salinity. You could also have mechanical stirring, so this is things like tides or libration or precession, which is basically you have some type of shaking motion that causes there to be fluid currents within the oceans themselves. And there's a new idea that was put out maybe a month or two ago that has this idea of magnetic pumping, so you could basically have Jupiter's magnetic field drive currents within Europa's ocean as well. So this is kind of an idea that's based on a lot of industrial applications where you can use magnetic stirring to mix iron alloys, for example. And today I'm going to focus on convection in the oceans as just one of these mechanisms, because I think it's important to consider all of these mechanisms kind of independently before you start to really lump them all together and really get a coherent understanding of the system. So we're going to focus on convection today. So now we can kind of dive into the meat of the talk, and we're going to start off using some rotating convection theory. And to do that, I want to start off showing just a really simple set of videos that illustrate how important rotation can have on your convective dynamics, or even just dynamics in general. So what we're going to show here is we're going to have two videos. This one here is just going to be a stationary tank of water, and we're going to pour creamer into it because creamer is more dense than water. And then over on this side, this is just going to be a similar tank of water that is instead rotating on a record player. So as I start both of these videos, we'll see the creamer get poured in. In this non-rotating case, it's denser, so it's just going to fall down towards the bottom of the tank and then spread out kind of like an inverse mushroom flute. But in the rotating tank, you get a really radically different flow structure where instead you have this axialization of your fluid columns. And that's basically just due to rotation causing everything to get vertically stiff around the rotation axis. So I really just wanted to illustrate with an example that you could do at home if you really wanted to, the importance of rotation and how that has a really dramatic effect on material transport within these types of fluids. Okay, so that's all well and good, but that's a pretty simple system. So how do you get to be something that's more close to a planetary regime? And this is a really active area of research. So one of the things that I wanted to point out is a number of experimental devices that are more complex that have a better representation of a planetary interior. So this is basically what their setups are going to be like. They're heated from below and cooled from the top to drive convection. And then they're this axial cylinder geometry, which has a similar gravity field as if you're near a polar region of a planet. And then it can rotate at a given speed. So there are many different devices. These two are at UCLA where I did my PhD. And then this is the largest one where this is actually a 4-meter high tank that is rotated and then heated. So that's really a way of trying to approach a more realistic type of parameter space, as I'll get into. But this is a really active area of the field to try to understand the influence of rotation on different fluid systems. So to give you an example of what some of these results look like, here I'm just going to show one case over here. This is the non-rotating case. And then the rotation rate is increased as you go towards the right in this plot. So in this non-rotating case, you basically have isotropic turbulence. So everything kind of looks the same no matter what direction you're looking at. And then as you start to increase your rotation rate, you get more and more of this axialization of the flow. So the rotation axis is aligned like this, and this really strong 2D nature of the flow is just due to the strong rotation and Coriolis force due to the rotation of the system. Okay, so then the next step in order to relate these types of experiments to planetary interiors is to use scaling laws. So I'll kind of walk you through this diagram since it's a little bit complicated. So I have two dimensionless parameters here. On the x-axis, this is what is known as the Ekman number, but the thing to think about this is that as you get to really low Ekman numbers, this is where your Coriolis force is stronger. So the Ekman number is basically a way of thinking about how strong your Coriolis force is. And on the y-axis is the Rayleigh number. And up here, at the larger Rayleigh numbers are basically where you have stronger buoyancy. So you can think of this as being a more strongly driven system. So it's kind of buoyancy versus rotation on this plot. And the thing to notice is that planetary interiors are in this far corner, so they're going to have the most rotation and they're going to have the most buoyancy. So they're isolated over here, and in a completely separate and opposite part of the plot are the experiments. So we're actually able to get to relatively low Ekman numbers and high Rayleigh numbers in the laboratory experiments that aren't really all that far off from the icy satellites, although they don't overlap yet. And the numerical models require they're a little bit more numerically challenging due to technological limitations, so they aren't quite as extreme values as these laboratory experiments. So what we want to do is try to use scaling laws to relate these two boxes since we don't have any direct overlap, so we have to use dynamical similarity. So what that basically means is if you want to know some property f that's a function of, say, this Rayleigh number and the Ekman number, if you're able to get this function, you can make a prediction about the behaviors of this, say, f property. So the f property that we're really interested in is the influence of rotation. So I'll go through a set of scaling laws that kind of show how that works. So the first scaling law that I want to discuss is the onset of convection. So everywhere that is in this gray box is where you have no convection. So it's basically just going to be stably stratified. And then once you get above it is where convection occurs. And the thing to notice is that this isn't a flat line. So actually, as you have faster and faster rotation, it's harder and harder to have convection onsets. Because basically, if you have this two-dimensional axis of flow in the system, you're going to have a harder time breaking and going overturning if you have just 2D flow. So that's why you have this upward trend along this profile. So as soon as you're able to have convection start, you're in this plume and columnar regime, which is basically where you have this really strong 2D axialization of your flow structures. And then as you either continue to increase your buoyancy forcing or you decrease your rotation rate, you're going to get into this next regime called geostrophic turbulence, where you still have some vertical stiffness of the flow, but much less so than in the previous two cases. So you really are limited to really axialized flow towards your boundary layers. And I have two lines plotted here, kind of this solid blue line and the dashed blue line, to reflect the uncertainty in where this regime transition occurs. So I wanted to kind of be honest and show the range in the literature of where we think that this transition occurs in this parameter space. So then kind of moving up to the next level of, say, higher buoyancy forcing, you get into this unbalanced boundary layer regime. And in this case, you've really started to lose all of your axialization in your bulk flow. And again, there's uncertainty in this regime transition in literature, so that's what these two lines are reflecting in the pink. And then the final part is if you force your system even stronger, so you have really, really vigorous convection, you're ultimately going to enter a regime that no longer behaves as if it's rotating, especially in the heat transfer sense. In this case, you really don't have any axialization on any scales, local or global, within your system. So in this case, we again have this range of potential transitions between the non-rotating and the unbalanced boundary layer regimes. So that's what this kind of red area is. And it's kind of unfortunate, as you'll see later, that this region is so large. So that's just something to keep in mind. So the next thing that you want to do is try to place the, say, icy satellite oceans on this plot to see what type of convective system you might expect them to fall into. And to do that, we need to have estimates of this Rayleigh number, which is defined over here, the Ekman number, which is defined over here, and then there's a third parameter, which I haven't really mentioned yet, which is called the Prandtl number, that basically describes the fluid properties. That is the other thing that you need to have to put those icy satellite oceans on this map. So to do that, the Prandtl number is actually the easiest of these to define, so that only relates on the kinematic viscosity and the thermal diffusivity of your fluids. So for the icy satellite oceans, this kind of ranges on the order of like 10. And we know that pretty well. The next number is the Ekman number. So this is, again, basically a measure of the influence of the Coriolis force on your oceans. So this depends on your kinematic viscosity again, and your rotation rate, and then your ocean thickness. And we can get ocean thickness from internal structure models. So again, this isn't too bad of a parameter to estimate. The real trick comes in when you have to estimate the Rayleigh number, which is on the top here. So this depends on thermal expansion. It depends on gravity, which is pretty easy. But really, the superadiabatic temperature contrast is really where the trick comes in. So that's why this is a relatively hard parameter to estimate. The ocean thickness, which you can get from internal structure models, the kinematic viscosity, and the thermal diffusivity. So I won't go into the details now, but in terms of the interior models, you can have self-consistent estimates of what the heat flux is, and then you can relate that to this temperature contrast, and then use the equation of state data for things like the thermal expansion coefficient. So we're able to get estimates using a combination of scaling laws, equations of state, and internal structure models for all of these different parameters. So the internal structure model that I use is based on Vance 2018, where they basically look at the icy satellites and they consider different ice shell thicknesses and ocean compositions, and then look at the internal structure models that are then going to be consistent with things like the gravity measurements that we have for these. So starting with Ganymede and Titan, the main things I want to point out here is not this really hard to read work, but basically that they consider 3 ice shell thicknesses. So they have cases where the ice shell is thick, so greater than 130 kilometers. They have a thin ice shell case where they have less than 30 kilometer thick ice shell, and then an intermediate case. And in each of these cases, this thick ice shell is going to have a relatively low heat flow, and then the thin ice shell is going to have relatively high heat flow. So they're self-consistent on that matter. And then they also consider a range of different ocean compositions, and the two that we're going to consider today are magnesium sulfate at a 10 weight % level, and then also pure water for comparison. And then for Europa and Enceladus, it's a fairly similar case, but in this time we're only going to consider 2 ice shell thicknesses. One is going to be the thick ice shell, so it's going to be 30 or 50 kilometers for Europa and Enceladus, versus a thin ice shell, so that's going to be 5 or 10 kilometers respectively. And then we're going to consider sodium chloride oceans at a composition that's roughly similar to what we have in the Earth's ocean, and also the pure water comparison. So we'll start off by adding our estimates for Ganymede, and this is going to be the case of the magnesium sulfide ocean. So again, there are 3 ice shell thicknesses, so there's going to be 3 vertical lines here. So this is going to be the case that is a relatively thick ice shell, so you're going to have a relatively thin ocean. So it's going to be at the relatively high Ekman number on this graph. Because you have a relatively thin ocean, you're going to have a relatively low heat flow, which is why it's a relatively lower Rayleigh number than these other cases. But you can see they generally follow along the same trend here. So when you add pure water, the difference is going to be shown in these dashed lines. So you can see it makes a notable difference in the case of a relatively thin ocean or thick ice shell, but a relatively small difference in the cases of a thinner ice shell case. So that's the case for Ganymede. And what that basically means is that all of these cases fall along this dashed red curve, which implies, depending on which one of these boundary scaling law estimates is correct, that you're either in this unbalanced boundary layer convective regime where you have 3-dimensional turbulence, or you could potentially be in this non-rotating heat transfer regime where you lose this axialization on both global and local scales in your models, or the oceans themselves. So that's the range that we predict for Ganymede. Then we can do the same thing for Titan, except now I add them in the black lines. So the solid black lines are going to be the magnesium sulfate ocean case, and then you again have the 3 ocean thicknesses, so this is going to be the thin ocean, and over here is going to be the thick ocean. And then the dashed lines are going to be the pure water case, and you don't see as much of a range in parameter space as you did for Ganymede. But you have a really similar prediction for how strongly the rotation is going to influence your convection, since it again kind of falls along this same red dashed curve. So that again predicts that you're either going to be in this unbalanced boundary layer regime or the non-rotating regime, depending on which of these scaling laws is correct. Okay, so next we'll move to Europa. So in this case, we again have the 2 ice shelf thicknesses, and we have the 2 ocean compositions. And actually, they're all both plotted right now. So you have only a small difference depending on the ice shell thickness, and you can barely even notice that there is a difference depending on what the ocean composition is. So whether it's salt water or pure water, it doesn't make a whole lot of impact in the regime prediction. So again, we find that Europa falls along this dashed red line, just like Ganymede and Titan. So that again predicts that it's either going to be in this unbalanced boundary layer regime or this non-rotating heat transfer regime. Okay, so the last case that we're going to consider is Enceladus. So these are smaller, so I'll just point these out, these two cases here. And this is going to, again, be the case where you have a relatively thin ocean or thick ice shell versus the thin ice shell and a thick ocean. So this is more appropriate for like the South Polar terrain, for example. And on this case, we only have two plots on this where there's actually no points plotted for this pure water case, and that's because there's actually not predicted to be any convection going on in the oceans. And that is a consequence of Enceladus being a relatively small body, so it has relatively low pressures. So here I'm showing the thermal expansion coefficient as a function of saltwater concentration in the ocean. So in order for you to have convection, you need to have this thermal expansion coefficient be positive, which basically means as it gets warmer, it's going to get lighter, so you have thermal convection driven that way. And I should mention that all of these estimates only consider thermal convection, so there's nothing related to compositional buoyancy sources in all of these estimates. So in order for this to be positive, you basically need to have ocean water that is, 0.36 molals of NaCl. So if you're fresher than that, it actually predicts that you're not going to have convection in the ocean. So that's why we only have the case of seawater that is plots on the diagram. So what that basically means is that for Enceladus, you're either going to be in this unbalanced boundary layer regime, or you're going to be in this geostrophic turbulence regime based on those estimates. And then I have this downward arrow to show, depending on what your sol contact is, you're going to have lower and lower thermal expansion coefficients, even if they remain positive, but that is then going to decrease your Rayleigh number, so that's going to then kind of bring it down on this diagram. Okay, so kind of wrapping those all together, what I'm showing here is a compilation of all of the estimates. Ganymede's in dark blue, Titan's in black, Europa's in kind of cyan, and then Enceladus is in green. And the things to notice is that Ganymede, Europa, and Titan all fall together on kind of this similar region of the plot. So you might expect them to have a similar three-dimensional convective turbulence type of flow structures, where on the other hand, Enceladus likely has a much stronger rotational constraint on the ocean convection properties. And before I move on to the next section, are there any questions? Yeah.
I'm wondering if you could comment on the latitudinal difference in the rotations and some of the sense will be different at the pole and at the equator. Does that affect what your model does?
So that's taken into account into the numerical models that I'll show. In the scaling laws, it is primarily based on the cylindrical experiments that I showed at the beginning. So that's not taken into account directly, but we've also compared those to kind of spherical geometries, and it seems to work pretty well too. So I don't think it's going to have too much of an influence on these predictions. And you'll see a little bit more in the numerical model part next. Okay, any others? Okay. All right, so next move on to some of these numerical models. So I use the numerical model MAGIC, which basically solves the Boussinesq thermal convection equation. So Boussinesq is basically just a way of saying incompressible. And it's in a rotating spherical shell, which is kind of shown by this geometry. So it's 3D. The lower boundary condition is hot. The outer boundary condition is cold to set up the thermal convection. And I also assume that the boundaries are stress-free. And then for simplicity, I don't include things like ocean tides or salinity gradients because I want to start off relatively simple in these models. And then what I do is I basically fix the fluid properties and I fix the buoyancy forcing, and then I vary the rotation rate across a sweep of parameter space. And for those interested, this is what the input parameters of the models are. And I use a pretty realistic shell geometry. And I'll just note that a lot of the results are really kind of largely insensitive to small variations in how thick the oceans are in the model. So kind of returning to this plot where you have buoyancy on the y-axis and rotation essentially on the x-axis. And again, here are the different convective regimes over here. And then here are the numerical models that I've run that basically span everywhere from the plume and column regime, although it's really more of like this geostrophic turbulence, up to the non-rotating regime. So I wanted to have a range of models that kind of spanned the range of possible regimes that we predicted from the satellites. So before I show some results, I wanted to kind of emphasize some details of the models. First is that we calculate these on a 3D spherical grid. And what I'm showing here is just basically a snapshot of your zonal flows. So these are going to be flows that go in the east-west direction. And this is going to be at the surface. This is going to be at the seafloor. And then you also just take a slice along a meridian, so the rotation axis is aligned here. So this is just at a snapshot in time. And then for these models, I'll also do a time average to try to get rid of some of this small-scale perturbations. And then many of the plots that you'll see next, I also vary over all longitudes. So when you see plots like this, they are averaged over both time and over all longitudes. So I just wanted to make that known up front. So we'll next go over how, across this suite of models, the zonal flows change. So I'll be giving these in dimensionless units, and I'll convert these to dimensional units later on in the talk. But basically, I want to say that this is basically your velocity that is normalized by the rotation timescale. So you basically, in this case, you have prograde flow, which is going to be noted by these positive values. So it's going to be eastward, westward, westward jets throughout the ocean. And these also extend all the way across the ocean depths. So that's one of the characteristics of the features in this model. And as you have slightly weaker Coriolis force, so this is going to the left on that diagram, you have a pretty similar flow structure, but you have one less band. So now you have a retrograde jet at the equator, and then prograde, and then high grade, or retrograde, or westward, again at high latitudes. And it's a slightly faster flow speed in this case. And then once you go even slower rotation, you get a pretty different jump here, where now you have a retrograde jet at the equator, and then prograde or eastward jets at high latitudes. But you have a big jump in your flow speeds. So you have much faster flows in this case. And then if you go to the next highest equine number, so again, you have even weaker Coriolis force, you have a really similar flow pattern in this case. And then in the last case, and this is the one that's in the non-rotating regime, you basically have your zonal flows that are concentric. So you have retrograde flow towards the top and then prograde flow on the interior to that. And again, the zonal flows are again weaker in this case. Okay, so that's the zonal flows, so that's east-west. What about north-south? So here I'm showing the radial circulations in this case. So this is the case that has the strongest Coriolis force, and in this case you might expect there to be more axialization with the rotation axis. And that's what you see, where you basically see all these features that are vertical in this case. And then if you decrease the influence of the Coriolis force just a little bit, you start to see a pretty different pattern, where you now have this really large concentration of upwelling fluid at the equator. But you still do see some axialization in your flow structures. And it's about an order of magnitude faster in this case as well. And then in the next case, we have a pretty similar case where you really kind of expand this concentration of equatorial upwelling, and then you have a concentration of downwelling on either side. So this essentially sets up like a Hadley-like Radial Circulation cell within the ocean. So it's upwelling, and then it kind of circles around in either hemisphere. And in this case, you again have a jump in your flow speeds. And it looks pretty similar in the next weaker Coriolis case, except this equatorial band is expanded. And then in the final case, which is again really similar to a non-rotating case, you just see basically patches of upwelling and downwelling fluid, which are kind of indicative of rotation not having a strong effect. So we can then look at the convective heat flux pattern. So this is basically going to be heat flux normalized to the average on this spherical surface. So this is again the surface, and this is the seafloor. But the main thing I want to point out is on the surface. So in this case, where the Coriolis force is strongest, you're going to have most of your heat flow coming out at the equator, and the least coming out, most of your heat flow coming out at the pole, and the least at the equator. And if you go towards slightly weaker Coriolis force, you again have some peak at the poles, but now you're now having a second peak at the equator, or third, I guess, where you instead have that warm upwelling water at the equator now has this signature that you see here. And then if you weaken your Coriolis force again, you're really going to emphasize this equatorial upwelling of warm water, so you really have a stronger peak at the equator. And that's again emphasized as you continue to decrease your Coriolis force. And then in the case where you don't have much of a rotational influence at all, you basically have warm and cool patches that basically drift over time. And because this is time average, what you basically see are these patches that are just smearing out as they get averaged over time. So in summary, we think that Ganymede, Europa, and Titan have really similar dynamics, and that they are most represented by these three numerical models, where you basically have retrograde equatorial flow and prograde flow at high latitudes, or you could have this concentric flow. You could either have radial circulations with a warm upwelling equatorial region, or you could have this patchy region, depending on how the influence of rotation, how strong that is, or you could have a really dominant peak in equatorial heat flux, or this patchy structure, depending on which of these models is correct. And then conversely, for Enceladus, we expect there to be a stronger influence of rotation, so we instead think that these two lower equinumber models with higher rotational influences are more applicable. So in this case, you would have a banded alternating jet structure for the zonal flows. You could either have this really rigid vertical flow structures or an equatorial upwelling. And then you're either going to have most of your heat flux coming out at the equator, or you're going to have three peaks at either pole and the equator, depending on which case is most appropriate. So that leads into the next session on ice-ocean coupling. So the main thing that we can look at is how these heat flow patterns will influence the ice shell in any material exchange. And the three ways that we're going to consider doing that is through ice shell thickness, through marine ice accretion, which is basically you're going to have different regions of the ice shell freezing and thinning, and then diapirism, which could be a consequence of this spatial variations in marine ice thickness, and I'll get into that. So to make this a little bit more quantitative, here are the heat flow patterns that I just showed you, but I also wanted to show you basically a dimensionless heat flux, so don't worry about the amplitudes as much as basically just the patterns as a function of latitude along the ice-ocean interface in the models. So for ice shell thickness, you might imagine where you have regions of high heat flow is where you're going to have regions of enhanced melting. So in that case, where you have your strongest Coriolis force, where you have the most heat flux heat being emitted out of the poles, you would expect to have polar thinning in this model. And then as you get towards this direction where rotation is less of a driver, you're going to have more and more enhanced heat flow at the equator, and you're going to have thinner ice at the equator in this model. So then you're going to have equatorial thinning, and in between you're going to have both polar and equatorial thinning in this case. And this one you're just going to have patches that are kind of with no clear pattern. So one thing to think about is if you're going to be generating large variations in ice shell thickness is to consider a process known as an ice pump, which acts on ice shelves in the Antarctic, where basically in regions where you have really thick ice, the pressure melting point is basically going to lead to melting along these regions. So it's going to have cold, fresh water that melts. It's going to travel along the base of the ice shelf, and it's going to get to regions where the ice shell is relatively thin and under lower pressure. So it adjusts the melting temperature that you're able to have reaccretion of this water in regions that are relatively thin. So it's basically a way of equilibrating your ice shell thickness variations. So then you could potentially have regions infilled with this marine ice that were previously thinned through the mechanism that I just talked about. So in that case, if you're able to refill these, you would then expect to have this polar marine ice at the most strongly rotationally constrained case, and then you're going to have more and more equatorial ice as you get to cases that are less strongly influenced by rotation. So one thing that happens when you refreeze this ice is that it's a really efficient stilling process. So that basically means that you're rejecting a lot of salts in this refrozen layer. And this has a consequence on compositional diapirism within the ice shell. So if you're going to have a region along an ice shell that is both warm and relatively fresh in material, so less salt, you're going to have, and it's less salt than the ice above it, you're going to have both thermal buoyancy and you're going to have compositional buoyancy. So you have two drivers that could potentially lead to diapirism within the ice shell. So in that case, you would then expect there to be enhanced diapirism where you have this potential marine ice accretion. So if you call it the next step in the sequence, then you would expect there to be polar diapirism in the case that has the strongest rotational influence, and then more equatorial diapirism in the case where you have less rotational influence. So that's kind of the sequence of possible ice-ocean coupling processes that we've been thinking about. So that's all well and good. Let's think about the satellites themselves. So there's a few observations that we can look at. One of the really exciting results that came out earlier this year is that there is a map of ice shell thickness for Enceladus, where it shows that the ice shell is relatively thick at the equator and thinner at the north and south poles, especially the south pole. And they're able to invert this to get heat flux coming from the ocean. So it essentially allows us to have a map of heat flux along the ice-ocean interface, which is really exciting from the modeling perspective. So if we look at our two numerical modeling results, we see that this pattern where you have the most strong influence of rotation is the most consistent with this heat flux pattern inferred from the topography and gravity measurements of Enceladus. So that seems to work out pretty well for Enceladus' case. So if we next move to Titan, where we have the next largest amount of data, we're able to do really similar analysis where you take the observed topography and you're able to convert that into heat flux coming from the ocean. In this case, you have a lot more patchy distributions of these features. So what Collaborators did is they basically took an average and only looked at the even zonal harmonics, thinking that that's going to be the most reflective of what an ocean contribution would be. So in that case, you have most of your heat coming out at the poles in this case. But if you look at our three numerical models, what you basically see is they predict most heat flux either coming from the equator or not to have much of a pattern at all. So that doesn't seem to be really consistent with this heat flux map. But remember that I haven't incorporated any compositional influences on these convective regime estimates. And one important consequence or aspect of that I haven't taken into account is that Titan's ocean is thought to be relatively salty. So the neglect of compositional buoyancy sources is actually a hindrance for our estimates. So if you're able to have a stable stratified, stable salinity profile, so basically one that has saltier water at the bottom and fresher water at the top, that basically means is that is going to offset any thermal buoyancy that you have. So that effectively means that you're going to reduce any buoyancy driving within the ocean itself. So that effectively reduces your Rayleigh number. So instead of being here, it would move your estimate directly downwards on this plot. So it would be a way of moving into one of the regimes where convection is more strongly influenced by rotation. So it kind of implies that you're going to have salt be an important aspect of the ocean dynamics at Titan. So in that case, we're able to match the observations, at least qualitatively. For Europa, we don't have any of these types of heat flux maps, so we're instead linked to things like surface geology. And one aspect that I'll point out is the distribution of chaos terrains, which are highlighted in these green regions here, where you have a concentration of these chaos features at low latitudes, then there's secondary ones up at high latitudes. And these features are not strongly, we don't have a great sense of how they form. There's many hypotheses, which is kind of summarized by the schematic down here. But one of the, I would say, leading ideas is that they're associated with diapirism. So that's kind of what you show in one of these. And there could be brine migration associated with that too. And the other aspect of this story is that we have maps of endogenic material from surface observations, and regions that have the most endogenic salts correspond to regions of chaos terrain, suggesting that they have kind of an internal origin associated with them. So then if you look at our three models, and remember that in models where you potentially have enhanced melting that's infilled with marine ice could have enhanced diapirism at low latitudes, which is consistent with these models, it suggests that these two models are most appropriate. And I'll also point out that there is secondary peaks, especially in this case at the poles, that could potentially be significant for these polar chaos features. And then finally, we can look at Ganymede. And in this case, we have even less data than we do for Europa. So the main aspect that I know of are these mass anomalies within the ice shell. We only have them for the northern hemisphere. So it's really hard to use any type of geophysical or geologic evidence to look for observational constraints on which of these models would be more appropriate. So it's, I think, still a relatively open question of which of these models is most appropriate for Ganymede. And then I'll just wrap up with two main points that I want to leave you with. And one are that ocean worlds are prominent in the solar system, and that it's really important to consider the ocean dynamics for their habitability, because we need to really focus on the possible exchange mechanisms. So you could have exchange from the seafloor up to the ice-ocean interface, and potentially from the surface of the ice shell down into the ocean itself. So I think understanding the ocean currents and the implications for heat flow and mass transfer is really important. And then the second aspect which relates to that is that convection can drive really strong ocean currents, and this can lead to spatial variations within mixing properties, within heat flow, and then all of these aspects can then have a consequence on the ice shell structures and dynamics within the ice shell itself. So I want to leave you with the best case model that I have for each of the satellites. So the first one is going to be Enceladus, and this is where I convert to dimensional units. So again, the east-west flows, we predict there to be a banded jet structure that has flows on the order of tens of centimeter flow speeds. And in the radial case, we expect it to be really axialized flow structures. In this case, you're going to have flows on the order of like a millimeter per second. You're going to have most of your heat flux coming out at high latitudes, and that's consistent with this new map of heat flux along the ice-ocean interface. And for the other body in the Saturnian system we considered, I think, again, that this same model is the most appropriate for this case, given this heat flux map. But in this case, the zonal flows are just a really comparable range compared to Enceladus. So that's going to be a few tens of centimeters. The radial flow speeds are going to be on the order of a millimeter per second again. And again, you're going to have this heat flux at the poles, which is consistent with the observations. But in this case, it assumes that we have a really strong compositional gradient across the oceans that causes there to be kind of a reduction in the buoyancy driving within the system. And then for Europa, we're predicting it to be this type of ocean model where you have retrograde flow at the equator, you have prograde flow at high latitudes, and here you're going to have pretty strong flow speeds of a few meters per second, so they're significantly faster in this case. You're going to have radial flow that's concentrated in these overturning, like Hadley-like radial circulation cells with equatorial upwelling, and then downwelling at higher latitudes. And on this case, you're going to have flows on the orders of tens of centimeters per second. And then in this case, because you have this really strong upwelling of warm fluid at the equator, you're going to have this band of enhanced heat flux along the equator as well, with secondary peaks that are much smaller at either pole. And this seems to be consistent with the distribution of chaos terrains, assuming a diapiric origin in particular. And then for Ganymede, we don't have a lot of constraints, so I picked the same one as Europa just for, because it's the lowest end of the region. We generally seem to be moving things lower on those plots, so it seemed to be a reasonable estimate. In this case, you're going to have flows that are potentially weaker but potentially stronger than what we predict on in Europa 2, and this is basically a consequence of the large range of uncertainty in the ocean thickness. So that's kind of the determining factor on the flow speeds here. And we again expect there to be this overturning circulation in the radial circulations that have similar flow speeds in terms of tens to 100 millimeters per second, high equatorial heat flow. And then we really need some more data to try to constrain this further in terms of looking at observations. And then just looking ahead, there are a few avenues for future research. One is to try to look at different boundary conditions, and this relates to, say, spatial variations in heat flow along the seafloor. So one of the things for Enceladus has been hypothesized that you could have a lot of heat coming out of the mantle that is concentrated at the poles. So it'd be interesting to incorporate that type of spatial distribution along the seafloor in our models. I think it's especially important to incorporate compositional effects. Again, kind of looking at Titan, where you need to consider the effects of salt. And then also try to become more and more extreme in our parameter values to really try to make these models approach the planetary estimates. And then also to do some more quantitative at looking at ice-ocean interactions and how you could influence the ice shell dynamics through ice-ocean coupling processes. And then also getting additional data through spacecraft such as the Europa Clipper mission, the JUICE mission, which is going to primarily focus on Ganymede, and then also hopefully Dragonfly at Titan. And with that, I'll take questions. Mm-hmm. So I have a backup slide where I don't think I have to go too far back, maybe further back than I realized, So one of the things that we had talked about in the meeting today is the possibility of using magnetic fields that are induced by currents within Europa's ocean as a way of doing like electromagnetic sounding of the ocean. So what it basically means is right now all of the induced magnetic field signatures are assumed to be due to Europa having a salty ocean that is then moving through Jupiter's magnetic field, where you could have an additional source where you have salty water that is then moving through convection that could also produce induced magnetic field signatures. So I think it would be really interesting to do a detailed study of what type of magnetic field signatures could result from this, fluid of salty material that moves, and see if that could create an induced magnetic field signature. So I've done a really back of the envelope estimate of this using Tyler's 2011 paper to make a scaling argument. And in this case, I only consider the Radial Circulations because you need to have a poloidal field that in order to be detectable through observations. So you want to have, I think that's most likely to create that form. And then also, I think it's worth considering a time average of the flow fields because then you're more likely to have a constant signal, which would be easier to distinguish between noise. So if I then consider this type of overturning circulation, I get a amplitude of about 3 nanotesla for this induced magnetic field current. So it's pretty small, but still something I think of interest that we could maybe use in the future. Yes, really small.
You can measure it.
Well, it's complicated now.
Why?
There's some changes on Europa Clipper for the magnetometer. I'm going to leave it at that.
Doesn't sound good. Alfred.
The branch material in Europa, one interpretation is that it's rich in magnesium sulfates that look like they're erupted from subsurface. But you didn't consider magnesium sulfate for Europa's ocean. Why was that, and what effect would that have?
So I didn't do that because I relied on the interior models from Steve Vance's paper, and they didn't include a magnesium sulfate ocean in their models. So I didn't have a way of self-consistently having the ocean thickness and the corresponding heat flow. So I could take the thermodynamic properties of magnesium sulfite and assume some range of ice shell ocean thicknesses and heat fluxes, but it wasn't as consistent as I would like it to be. But that's why I didn't consider magnesium sulfite for Europa.
He's published papers with magnesium sulfate.
He has.
Considered other papers.
Right, yeah.
It's not like he rules it out.
No, he didn't rule it out, but that's just not what he included in that paper.
The heat flow, weren't there kind of details, they're not maps? I forget the name of the instrument, but by the Spencer group.
Sears.
So
So there are some heat flow maps, especially for Enceladus and Titan, like I showed. But in this case, I'm really looking for a global value that is consistent with ice shell thicknesses and different ocean compositions. So I'm trying to get a range of what could be happening. And as far as I know, the numbers in Steve's paper are roughly consistent with the heat flow maps that have been observationally derived.
those heat flow maps are from temperature.
So the two that I showed for Enceladus and Titan are primarily derived from topography and gravity measurements, and then they assume heat is transported through the ice shell and take into account things like erosion in order to figure out what kind of heat flow is necessary to produce that range of ice shell thicknesses and spatial variations in those. I hope that makes sense. Yeah.
For Enceladus, a big bucket of land is argued that you have relaxation of craters in areas outside the south polar ring.
Right.
Areas of high heat flow in the past. Is that more difficult to explain, or if you go shell rotation?
In just the ocean context, that's a little bit harder to explain. But I was on a paper a few years ago that kind of looked at the idea that you could have true polar wander have happened. So there are two regions of Enceladus that also show regions of like enhanced tectonism that are antipodal to each other. And we think that if Enceladus had done a true polar wander event, those regions would have been at the poles, which would then be more consistent with this model. And you could also relate that to potential processes within the ice shell in terms of convection, because you're going to need to take into account things like how surface temperature varies as a function of latitude, which turns out to be actually be important, and then also how you're going to have the influence of tides, especially tidal heating being amplified at the pole. So I think a combination of all of those things may help explain those other regions on Enceladus that look to be tectonically interesting and have higher crater relaxation rates there.
Yes, I was going to ask you, how do the ocean heat fluxes compare to tidal heating in the shell? That's the magnitude.
Are you thinking the magnitude from my models particularly, or in terms of just
Just roughly, are they comparable or smaller or bigger?
the top of my head? I don't know. But I will add the caveat for these models. You know that they're not in the same parameter space as the satellites. And what that basically means is they're over viscous. So they're basically more like tar than like water. So in order to have convection actually occurring, you need to have them being strongly overdriven as well. So then if you overdrive your system, you're going to have kind of bogus heat flux numbers. Then you have to take that into account. So there's a reason I always use dimensionless numbers, because even though they look ridiculous, they're not actually once you scale them out to the right parameter regime. But I want to make that kind of caveat known.
But I think Isamu's point is that most of the models show most of the tidal heating occurring in the shell.
Oh, yes.
The ocean temperature that's affecting most of the heat flow.
Right.
So
No, that's a fair point. And a lot of these models take into account, I believe, those types of tidal contributions. And there's been more and more work, especially for Enceladus, that suggests that there could be a significant contribution from the deeper interior as well, especially if it's like a fluff ball, for example. So I think that there is even enough heat with radioactivity that you could drive pretty strong convection. Because that's what a lot of these thin ocean cases, the heat fluxes associated with those models are roughly in line with some of the radiogenic estimates. So even if you don't include tidal heating at all, it still boosts you up into that pretty strongly driven regime.
So the topography inverted heat flux map that you showed for
Mhm.
Titan, before zonally averaging looks more like the splotchy, non-rotationally constrained
Right.
case. So I'm wondering about the validity of doing that zonal average.
So I've been wondering about that as well. So I don't have a great answer other than that I think that's a totally valid thing to consider. My one hesitation to that is that you really need to have pretty strongly driven convection, and it entirely depends on which of those scaling laws is the right one for you to be in that regime. And all of the other models seem to have a preference to go lower in effective Rayleigh number rather than higher. So if there's, say, an influence of salt, that would tend to move it down, not up. So I think that that's kind of why I preferred to go down rather than kind of argue for this patchiness, but I definitely thought about it.
that global topography map of Titan is 99% interpolation.
Fair enough.
All right, I have one question.
Yep.
How could these things evolve, over a long time, like a billion years? Because you've got a lot of mass transfer going on, and
Right.
compositional variations, and it seems like it might either reach some steady state and be all homogeneous or be totally chaotic. And have you thought about that or anything like that?
So I haven't really looked into it that much, but what my understanding is that you could potentially have kind of cyclic variations in ice shell thickness. So you could potentially have it, thin, 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 thin up, and then it's going to become, say, conductive ice shell, and then you're not going to emit your heat as efficiently. So eventually it's going to thicken, and then it's going to convect again, and then it's going to thin and thin and thin, and then it's going to reconductive. So you could basically have like a cyclic nature in ice shell thickness. So I think that's something to think about over the evolution of those bodies, but I haven't taken that into account in any of these models. But it's interesting to think about, especially in terms of like the isolation coupling processes and how you could have different remnant signals of that potentially in the ice shell, or different eras of geologic activity that could be reflected on the surface.
Right. Okay, if there's no more questions, we'll give Krista another round of applause.
All right.